Hello. So in this presentation, I will introduce one of the most influential developments in modern machine learning, the transformer model. As proposed in the landmark paper, Attention is All You Need. This architecture has fundamentally changed how we approach natural language processing, powering models such as BERT, GPT, and many others. Let's begin with some context. Many tasks in natural language processing, such as machine translation, text summarization, and question answering, involving sequence transduction. The task of mapping one sequence to another, these problems require a model that can understand the order, structure, and dependencies between elements in a sequence. Traditionally, this challenge was addressed by using recurrent neural networks, which process sequences one element at a time, maintaining a hidden state that captures information from previous steps. Later, the long short-term memory networks, which is a special type of RNN, were introduced to better handle long-range dependencies by manipulating the vanishing gradient problem through gating mechanisms. However, both RNNs and LSTMs suffer from inherent limitations. Their sequential nature makes training and inference time confusing. And even with LSTMs, it remains difficult to model long-term dependencies in very long sequences. In 2017, Vaswani and his collaborators proposed the transformer architecture in their paper, Attention is All You Need. This model completely removed recurrences from the design and instead relies entirely on self-attention mechanisms. This innovation not only allowed for better modeling of long-range dependencies, but also made the architecture highly parallelizable, significantly improving training efficiency. So, why is attention important? In natural language, the meaning of a word often depends on another word in the sentences, sometimes those that appear far away. And traditional models like RNNs and LSTMs propose sequences one token at a time and must rely on memory carried across many steps, which can cause important contextual information to decay or vanish. This makes it difficult for them to capture long-range dependencies effectively. The attention mechanism addresses this problem by allowing each word in a sentence to dynamically focus on other relevant words, no matter how far apart they are. For example, in the sentences, the animal didn't cross the street because it was too tired. The model needs to understand that it refers to the animal and not the street. So the attention mechanism helps make the connection directly. Moreover, attention enables all parts of a sequence to be processed simultaneously rather than sequentially. This parallelization leads to a significant speed improvement during training and inference, making a model much more scalable. In short, attention improves both the accuracy and efficiency of sequence modeling and is the key to the success of the transformer. The transformer allows an encoder-decoder structure, which is a common architecture pattern used in sequence-to-sequence tasks such as machine translation. This architecture is designed to map an input sequence to an output sequence of potentially different lengths. The encoder is responsible for reading the entire input sentences and converting it into a sequence of rich hidden representations. It does so through a stack of identical layers, such each containing a multi-head self-attention mechanism followed by a position-wise feed-forward neural networks. These layers allow the model to capture relationships between all tokens in the input regardless of their position. The decoder, on the other hand, also consists of stacked layers, but it has two sources of input, the encoder's output and the previously generated token from the output sequence. This design enables the decoder to both attend to the context and of the input sentences and maintain coherency with what has already been generated. Each decoder layers includes a masked multi-head self-attention block, ensuring that predictions for a given position only depend on earlier positions, followed by an encoder-decoder attention layer and a feed-forward network. This structure allows the decoder to incorporate relevant information from both the input and the potentially generated output. Together, the encode and the decoder allow the transformer to efficiently and effectively generate high-quality output sequence. The use of self-attention throughout enables better parallelism, richer contextual representations, and a more flexible modeling of sequence dependencies. At the keystone of the transformer lies on the concept of self-attention, a mechanism that allows each token in a sequence to directly interact with all other tokens. Regardless of their position, this enables the model to capture contextual relationships with much greater flexibility and precision than traditional architectures. The process begins by projecting each input token into three different vectors: a query, a key, and a value. These vectors are linear transformations of the original token embedding. The query representation represents the current word's intent to seek relevant information. The key encodes the identity or signal that each word provides, and the value carries the actual content to be retrieved. To determine how much attention one token should pay to another, the dot product is taken between the query of the current token and the key of all tokens in the sequence. This results in a set of raw attention score are then scaled and passed through the softmax function, yielding normalized weights that sum to 1. Those weights are used to compute a weighted sum of the corresponding value vectors, and the result is a new vector representation for the current token, which is the one that reflects not just its own embedding, but also includes contributions from other tokens deemed relevant by the attention mechanism. In fact, self-attention gives each word a dynamic context-aware embedding based on its relationships with other words in a sequence. This allows the model to capture subtitle dependencies such as subject-verb agreement or coremphasis resolution, which are crucial for understanding natural language. So this formula represents the core computation in the self-attention mechanism. For every token in the input sequence, the model calculates how much it should attend to every other token, including the self. To do this, we start by computing the dot product between the query vector and the current token and the key vectors of all tokens. This operation produced a set of similarity scores. If a query aligns closely with the key, the resulting score will be high, and vice versa. The higher the score is, will indicating a stronger relationship between those two tokens. However, those dot products can grow large in magnitude, especially when the dimensionality of the vectors is high. The model scales the score by dividing by the square root of the key dimension. This scaling prevents the softmax function from producing extremely peaked distributions, which can make learning unstable. Once scaled, the scores are passed through a maxsoft function, which converts them into a probability distribution over all tokens. These are known as attention weights. Each weight represents how much influence a given token should have when computing the current token's new representation. Finally, the model uses these weights to compute a weighted sum of the corresponding value vectors. The result is a single output vector that represents a context-aware version of the original token, one that incorporates relevant information from other tokens and weighted by their own their importance. And mathematically, this entire operation can be expressed by the formulas shown in the slide. This compact formula summarizes how self-attention integrates global context efficiently and effectively. To enhance the model's capacity to capture relationships within an input sequence, the transformer architecture introduces multi-head attention. Instead of performing a single attention operation, the model runs multiple attention mechanisms in parallel. Each with its own set of learning projections of query key and value vectors. After computing attention separately in each head, the results are concatenated and passes through a linear projection layer. This allows the model to integrate multiple perspectives into a single representation, improving both its expressiveness and flexibility. However, there's one challenge with self-attention. It is inherently in order agnostic. In other words, without any additional mechanism, the model has no way to distinguish between sequences like the dog chased the cat and the cat chased the dog. To solve this problem, the transformer incorporates position encoding, which injects information about the position of each token into its input embedding. This approach allows the model to capture both absolute and relative positions in a sequence. Together, multi-head attention and positional encoding allows the transformer to simultaneously understand what word means and how they are related to one another and where they appear in a sentences, all information that is critical for natural language processing. So each encoder blocks in the transformer consists of two main components, a multi-head self-attention mechanism, which we just introduced earlier, and a position-wise feed-forward neural network. These are followed by two crucial techniques, residue net connections and layer normalization, which help stabilize training and preserve gradient flow. The feed-forward network, which is applied independently to each position, allows the model to learn more complex transformations beyond linear attention. To improve training stability and convergence, the transformer applies residue net connections around each of these two sublayers, and meaning the original input is added back to the output of the sublayer before normalization. The layer normalization that follows helps mitigates issues like internal covariance drift and leads to more stable training dynamics. The decoder shares much of the same structure as the encoder, but with a few important differences. So first, it uses masked multi-head self-attention, which restrict each position from attending to future token in the output sequence. This is essential for autoregressive generation, ensuring that the model only has access to already generated tokens during training. That's preserving causality. Second, the decoder includes a encoder-decoder attention layer, which allows the decoder to attend the encoder's output. By combining those three types of attention, self, masked self, and encoder-decoder, the transformer decoder can effectively generate coherent and contextually grounded outputs. So the transformer model brings several important improvements over older models like RNN and CNNs, especially for processing sequence such as sentences. One major advantage is that information can travel more directly between words, no matter how far apart they are in the sentences. Just in comparison, in RNNs, the model has to read one word at a time, so information from earlier words takes many steps to reach the later ones. This makes it hard for the model to understand long-range relationships, but with transformers, every word have a hidden connection between with all other words at the same time. Another big benefit is that transformers don't rely on step-by-step processing like RNNs. So this means all the words can be processed in parallel, which makes training much faster. Also, because there's no recurrence, the model design is simpler and easier to scale. This advantage helps explain why the transformer has outperformed older models in important tasks like machine translation. So as you can see, the in the screenshot that the complexity of a per layer is much less for the self attention than recurrent or convolutional neural networks, which makes it train much faster. So the real-world impact of the transformer has been remarkable and far-reaching. When it's the first introduced, the transformer model set new record in machine translation performance. So as you can see in the screenshot, that transformer only took 28.4 and also 41.8 as the overall score in translation from, I believe it's English to German and English to French, which outperform all other older models, and also the training cost, each significantly slower than other models. So these improvements were not only about performance, the model also influence how people in the general in current times think about how to do natural language process. So the transformer architecture quickly become the founder of the all major natural language processor models we use today. So like BERT is built from the encoder part of the transformer and is now widely used in search engines and question answering systems. And also GPT, including the Chat GPT, um, is based on the decoder half of the transformer and revolutionized natural language generation. Models and like and many other models are on transformer-based structure to push the boundaries of language understanding and generation. Beyond performance benchmarks, the transform architecture reshaped the entire NLP landscape. It brought a new era of pre-training, fine-tuning, and transfer learning that made powerful language models accessible and practical across industries. Um, in short, the transformer was not just better model, it became the new standard in AI. Yeah, that's my presentation. Thank you.